In this video, I'm going to discuss colligative properties. So, colligative properties depend only on the amount of solute, not the identity. So there are four major colligative properties that I'm going to go through in this video, and they're the ones you'll most commonly see. So number one is going to be freezing point depression. So the addition of a solute to a pure liquid reduces / lowers, depresses the freezing point of the liquid. An example would be water. Usually its freezing point is 0 degrees Celsius. If you add in a salt like they do to the road to prevent it from icing over, that lowers the freezing point. So that's the reason salt is added to icy roads or roads that could become icy, because it makes it so that water will freeze at a lower temperature. So hopefully ice won't form because it takes colder temperature for that ice to form. And the more salt you put down, the colder that temperature needs to be. And the equation to know exactly how much the freezing point will be depressed is given as follows. So the change in the freezing point is equal to I KFM. Now, I is the Van 't Hoff factor, which usually we'll estimate. Sometimes you'll be given the exact value of it, but in general, you'll estimate it from whatever solute you're adding in. KF is the freezing point constant. In this case, for water, which is most often, it's 1.86 degrees Celsius per molal for water. And then M is the molality of the solution. So with the Van 't Hoff factor, it basically is saying how much your solute dissociates. So if I have NaCl, the Van 't Hoff factor is 2, because it breaks into sodium plus and Cl minus. If I have, glucose, this is just going to be 1 because it's not an electrolyte, right? It doesn't break apart in solution. Something like calcium fluoride, I would equal 3 because you have Ca2 plus and 2F minus. So that's how you calculate the Van 't Hoff. So the more the solute breaks up, the greater the Van 't Hoff factor, so the greater the freezing point depression is going to be. Since it is a depression and it will be a negative sign, often a negative sign is included right there, but just know that your freezing point is always going down, no matter what solid you add in. Number 2 is boiling point elevation. So with this, the addition of a important here non-volatile so the addition of a non-volatile solute to a solution increases the boiling point. And by non-volatile, that's something that doesn't easily go into the gas phase. So here, think of a salt, or like glucose, sucrose, anything like that, that's not volatile. So when you go to boil water, say to make pasta, you often put salt in the water. What that does is it raises the boiling point so that your pasta cooks at a higher temperature, and that way it doesn't take as long. So that's just an application of the boiling point elevation. And this whole boiling point elevation can be explained by Raoult's law. So Raoult's law says that the vapor pressure of a volatile solvent above the solution containing a non-volatile solute is proportional to the solvent's concentration in the solution. So that's wordy, so I didn't want to write down the entire definition, but you can understand the definition from the equation for Raoult's law. And that equation is that the vapor pressure of the solution, or the vapor pressure of the gas above the solution, right, is equal to the mole fraction of the solvent times the vapor pressure of the pure solvent. So again, the vapor pressure above the solution is equal to the mole fraction of the solvent times the vapor pressure of the pure solvent. So the greater the amount of solute you add into a solution, the smaller the mole fraction of the solvent, and that means you have a smaller vapor pressure above the solution. Now you can also write this equation in terms of the change in vapor pressure. And that would be delta P, so the change in vapor pressure is equal to the mole fraction of the solute times the pure vapor pressure of the solvent. So it's basically the same equation, but it changes the mole fraction from the mole fraction of the solvent to the mole fraction of the solute, and it switches just the pressure of the solution to the change in pressure. Wherever the major application of Raoult's law, again, is that when you add in a non-volatile solute to a solution, the vapor pressure of the solvent above the solution goes down. Okay. Continuing with the boiling point elevation, there's an equation just like there is for the freezing point depression. And that equation is that the change in the boiling point is equal to I kb m. So again, I is equal to the Van't Hoff factor. Kb, this is going to be the boiling point constant, and it's going to be different for every solvent. But for water, it's 0.51 degrees Celsius per molal. And then m, again, is molality. So notice here that for water, at least, the Kb is a lot smaller than Kf is. So in general, it takes more solute to be added into a solution to increase the boiling point than it takes to decrease the freezing point. All right, last one I want to go over is going to be osmotic pressure. Okay, so certain materials are semi-permeable and only allow certain molecules, often very small like water, through. And in this case, the solvent always moves in the direction of higher salt concentration. So here's an example. We got a tube here. We have a semi-permeable membrane right there. On both sides, we have equal volumes of water. There's 4 solute particles on the left and 10 on the right. So when this reaches equilibrium, the solvent will move to reach equilibrium in terms of equal concentrations on both sides of the membrane. We still have 4 solute particles on the left and 10 on the right. But the water level's gone down on the left and it's gone up on the right. Draw it a little further up so it matches kind of what's next to it, right? So it goes farther up on the right and lowers on the left because water moved from left to the right to balance the concentrations out. So the solute particles cannot move through the membrane, only the water can to balance the concentrations on each side. Now there's an equation for something called osmotic pressure that we can calculate. And the osmotic pressure is the pressure required to stop osmosis from a pure solvent to a solution, and it can be calculated as follows. So that is osmotic pressure is equal to mRT. And this is equal to N over V times RT. Right, so the M here is the molarity, right? And the molarity is the same thing as moles per volume. R is just the constant 0.0821. And then the temperature, or T, is temperature. So that is how you calculate osmotic pressure. So I went through each of these different colligative properties, but the biggest takeaway with colligative property, again, is that it doesn't matter what the identity of the solute is. Adding in any solute is going to increase the boiling point, going to depress the freezing point. Any non-volatile solute will lower the vapor pressure of the solvent above the solution. And with osmosis, it doesn't matter what those solute particles are. Water will always move through a membrane to balance the concentrations on both sides of the membrane.